All right, ladies and gentlemen, this is it. Module number 9, Logistic Regression. We have finished the course. We have reached the end. Again, the quiz for this is totally optional, and I will not include any questions about this module in the exam. This is just for your information, for your introduction. Remember, this is just to introduce you. I don't expect you to be an expert in biostatistics, though many of you have shown quite the ability to think in biostatistics terms through the exams. So good job there. Okay, so introduction. Logistic regression generalizes methods for two-way tables. So remember, two-way tables, I kind of showed them to you like this, that each cell was A, B, C, D, and that you have, for example, a test being positive and negative, and then the disease status being true or being false, not having a disease. And from this, we can get things like positive predictive value, negative predictive value, etc. And you can do this with these 2x2 tables. But when you're doing this for multiple things, not just disease, but then age, you have to make tables for each age group, things like that. Then that's a lot of math, right? So you gotta bring in the computers and do a logistic regression. So it's similar to linear regression, but the details are different. That the response variable is categorical, yes or no, 1 or 0, true or false, big or small, things like that. The model is not estimated via minimizing least squares. It uses whole other methods, and the coefficients have a different interpretation. So here's an example. Patients admitted to intensive care units are very ill, either from a serious medical event or from trauma. Can patient features available at admission be used to estimate the probability of survival to hospital discharge? In the ICU dataset in a Plory 3 packages from a study conducted at Bay State Medical Center. The dataset contains information about patient characteristics at admission. So you have things like heart rate, diagnosis, and kidney function. And then died or lived. So here's your two things, 1 or 0. Here they have it as 1 for survival and 0 for death. But that's what I'm trying to get at. You have one or the other. And so, you let R do the thing for you. And so the odds of survival for those who did not receive CPR are 467. And the odds of survival for those who did not... and the probability is 82%. Right, and here you have two different things. You have odds and you have probability. And notice a 2x2 table here. Okay. So this is something you need to know just in life. a little bit of algebra tells you what probability is. Odds to probability and probability to odds. So from the previous example, the odds was 4.67 and the probability was 82%. And it's because we just did some algebra and came up with these numbers. So you'll see that probability being 0, your odds is 0, but probability almost 100%, your odds is almost infinite. And look at the association here, right? You go from 1 in 99 to 3 in 1. So 3, and if 4 equals 1, it's 3 in 1, right? So think of odds as the probability of something happening to the probability of something not happening, right? If the chance of something happening is 30%, then the chance of it not happening is 70%. And this is how we do odds, 3 to 7, okay? And that's more or less how this works. So in simple logistic regression, you see that Y is a binary variable and X is a predictor variable. An ICU example, survival to discharge, and CPR. So the probability of X is the probability of surviving given that something, right? Goes back to Bayes' theorem, where Y denotes survival. And so here the log odds, we use the log odds, and I'll explain why in a little bit, is this is a line just like the other ones, right? Why log odds? Well, logistic regression is based on modeling the association between the probability of the event of interest occurring and the values of the predictor values. But a probability can only take values from 0 to 1, right? You can either be alive or dead, 0 to 1. So it's not as ideal as a response, and so the odds ranges from 0 to infinity. So when you're graphing it, when you're graphing probability, you can only do 0 or 1. And so depending on your other variable, everything would be either up here or down here, and you cannot draw a line through that, right? It's not doable. When it comes to just odds, your range is 0 to infinity based on this. But what if we want to know if there's something down here, right? It just stops right there. And so again, we need to convert it. And so when we do the natural log of odds, then it becomes negative infinity to positive infinity on the y-axis. And then you have your x. And now we can draw nice lines that don't stop at the origin. So of course there's some similarities with linear regression. The right hand side of the model looks the same, but there's no residual error. Remember at the end we used to add this little residual error. So logistic regressions don't have a residual error, no residual error term. The difference is that logistic regression is used to calculate predictive value of log odds, which you need to convert back. So the natural log of the odds, the way to get it back to odds is to raise the whole thing to e. E raised to that gets rid of these two, cancel out, and you have odds. The GLM function is used to estimate a logistic regression model and requires an additional specification in the argument family binomial link logit. Otherwise, it will not work for you. You will get all sorts of errors in your R code. So here you have it: family binomial link logit. Your CPR and your survival, your data, and you see your intercept when CPR equals no is 1.54. So your odds, your log odds of survival when CPR equals 0 versus your log odds of survival when CPR equals 1 go down by this much. And it makes sense, right? If you receive CPR and you end up in the ICU, chances are you're pretty bad off and your survival is not guaranteed. Whereas if you weren't sick enough to need CPR, then you're probably going to be healthy enough to survive. Okay, and this is how you interpret the output. Remember that probability of x equals the probability of y equals 1 given x equals x. Probability of survival equals 1 given that you have CPR. So the log, the natural log, and sometimes I write natural log as ln, L natural, and that's how your calculator has it. Log of the probability of living given that you were given CPR versus the probability of not living given that you were given CPR. And so when CPR yes is equal to 0, you were not given CPR, then this is your natural log odds, again, of surviving. Then you need to raise it to the exponent. See, right here. Okay. The slope coefficient represents the change in log odds from the no to the yes. Okay, so when you have yes, x equals to 1 right there, and then when you have that there. The slope coefficient is a log of the estimated odds ratio of survival. Why? Because when you subtract one log, it's the rules of logs. When you subtract one log from the other, then you just end up with dividing them both. So here you're subtracting this from this, and so you just divide it, and this is your log odds ratio. And so you already exponentiated, so it's not the log odds ratio, it's actually the odds ratio. So you have about 82% less odds of dying if you did not require CPR. As with linear regression, where the slope captures the information about the association, same thing. Your null hypothesis is that the slope is that the line is nice and flat. Your alternative is that it is not flat, it is either going up or going down. The chi-square test does not directly show the direction of a significant association. If you just do the table, you don't know the direction. You don't know that for every increase in x, you get an increase in y. You cannot get that from this. But a logistic regression gives a numerical estimate of the size of an association. A two-way table cannot be used with a numerical variable. And then a multiple logistic regression, as you can imagine, is just adding more terms to the right-hand side here, all the way up to here. And so the coefficient estimates and the change in log odds for a 1 unit change in that variable if the other variables do not change, and the difference between the two of them is the log odds ratio, and then you just exponentiate that to get the odds ratio, or the difference in odds between two groups. So always remember to exponentiate these to actually turn them into odds, and then you can from there turn them into probabilities. When you're doing a lot of models, you want to use Ikaiki's information criterion. Just, it's analogous to the adjusted R squared, just to tell you which model is the best one. A lot of times we throw a lot of variables into a model and it gets all confusing, so we just look at a AIC. A lower AIC is indicative of a more parsimonious model, a model in which the predictors are better fit. Same thing, the inference is that, the variables X and Y are not associated, and the alternative is that they are. And how do we do that? Well, when we look at our coefficients, we look for that ever nice p-value. So in terms of the odds ratio, by the way, if an odds ratio is equal to 1, then the odds of the two groups are the same, right? A number divided by itself is always equal to 1. An odds ratio that is not 1, that means that the odds of the two groups are different. That would be your alternative. So your null would be that the odds ratio is 1. Your alternative is that the odds ratio is not equal to 1. Overall goals are similar to linear regression, estimating the association between a response and several predictors, assessing statistical significance of the association. But in logistic regression, association is captured through odds and log odds instead of the mean of a response variable. Logistic regression can be thought of as an extension of two-way tables, just as linear regression can be thought of as an extension of two sample t-test and ANOVA. And that's it, ladies and gentlemen. Questions, comments, concerns, you know how to get a hold of me. But this is it. This is the end. You have reached the end. Thank you so much for a wonderful, wonderful term. I hope you are all staying safe in the pandemic. I will continue to post videos for the walkthroughs, for the quizzes, and then the final exam will be 75 questions, all electronic. You won't have to submit any code or anything. It's just multiple choice, true or false, matching, etc., like that. It will open May 3rd. And be open until the last day of classes, when you need to turn it in or you need to finalize it. Okay? So that's it. Thank you so much.